Okay, so hello everybody, welcome to our second lecture. Before actually going to the second lecture of Hadronic Physics, I will go very quickly a reminder of the first part and finishing the last part of it. So we have seen that in order to model hadronic interaction, we cannot use the underlying theory, although it's well known at QCD, but we have to rely on models, hadronic models. And we need several of them because they are based on different approximations, different ideas. We need to use some of them. In particular, is important the energy range where this hadronic model are actually used. And there are four main categories of models that we need. A high energy, the string model, where we model things in terms of constituent quarks. The intranuclear cascade model, where we see the nucleus, target nucleus as a bunch, an assembly of proton and neutron. And then on the bottom part, we have nuclear physics, a first part where we have excited fragment far from the equilibrium. And then the last part, we will have an excited nucleus in a thermodynamic equilibrium, but not in the ground state, and then we'll go to the ground state. We have seen this important separation between the hadronic cross-section and the final state. So the hadronic cross-section tells us how far an hadron will go until it will undergo to an hadronic interaction. And the final state model will tell us what is produced by that interaction. So which particle, how many, and their property, the direction, their kinetic energy, and so on. We have seen the framework, so we can have as many cross-sections as we want, with the idea of putting more refined and precise cross-section for per specific case, and we pick the last one with the hope that is the most precise for that particular configuration of particle type, energy, and target nucleus. For the final state, we need to have at least one model, not fully overlapping, like here. So this is considered an error. But we allow this situation where there is a transition region between the two. And the idea is to draw a random number in this transition region and select according to a given probability, which goes linearly. It is assumed to change linearly, which of the two models to pick for each interaction. We have seen that in general, in hadronic physics, there are two processes which compete, elastic and all the rest, which is called inelastic. Let me skip this one. Neutrons, we will come back today. So physics list we have discussed a lot. It is important in the physics list that we choose the main hadronic models, and there are different choices according to the kind of physics that we want to describe, how accurately we want to describe. And then we were discussing validation. So the point, this is where we were stopping. So as I said, these hadronic models are complex. There are several of them, and also code-wise, it's quite big. You know, Gen4 is more than 1 million of lines of C++ code. And there is plenty of room for mistakes, of course, so in the implementation. So validation is very important. And I said that there are two types of validation. One, which is called thin target or microscopic or single interaction validation, which is one made by the developers of the hadronic model, where there is a well-defined interaction, and we look at what is produced experimentally, and we compare with the theory, with the simulation results. I will show you in a second. And then there is a second one, which is for the user to take a complete physics configuration, able to handle all the cases. And typically, in the high energy context, these are essentially calorimeter test beams And I will show you an example. So yeah, so this is the thing I would like to show you and spend some words, an example of this model level thin target test. So this is one of the string model, FTF, the free of string model. And we are validating with some data. HARP was an experiment, a fixed target experiment made here at CERN 20 years ago. And you see here an example. So we are here, we have proton impinging on a thin target of tantalum, producing, and we are looking at the inclusive production of pi minus. All the rest, if other particles produce, we are not interested. We just look at the production of pi minus. And we are looking at this production in different angular region of these pions respect to the incoming particle. And we are plotting here the transverse momentum with respect to the projectile direction of this pi minus. You see different set of points because there are different energy. So this proton, there are some data 3 GeV, 5, 8, 12, and 15. And for each of them, you see in different colors the histograms, which are the simulations. And this is really the results after several years of effort and even after some tuning, because these hadronic models have some parameters that can be tuned from experimental data. Of course, there are much more experimental data than parameters, so we cannot fit everything perfectly because the parameters are 10, 20 parameters, then the data are 100,000 of them. So this is really, if you want, state of the art of the model. And you see that, yes, more or less, the simulation trying to describe the data, but you see that there are discrepancies. And this is actually always the case for hadronic physics. So we rarely show validation of electromagnetic physics because typically the precision is a % level and is on top of the data. You will think that we are fitting the data, but electromagnetic physics is precise at the % level of most observables. Whereas for hadronic physics, really state of the art is that we can describe things according to what we are looking at 5, 10, 20%, 50%, sometimes a factor of 2 from the data. And this is the best we can do today. And now let me show the validation that the user, of course, again, in the context of high energy experiment. So these are 4 different test beams setups, 3 of them from Atlas and 1 from CMS, made 20 years ago. So what is a calorimeter setup? Is a kind of small slice of a real detector that is built before building the whole experiment, the whole detector, for 2 purposes. The main one actually is to see that you can build it, how the DRQ, the electronics and everything is working. But then you can also use it for physics validation to see what is the physics list, the components of the physics that you need in order to describe your data. And typically, these are the variables. So typically, in a calorimeter, what you are checking is the property of hadronic showers. And properties are like the energy response, energy resolution, the profile of the shower, longitudinal means along the direction of the incoming beam, which started the shower, or laterally in the transverse thing. And I wanted to show you this thing where the variable that we are here is Atlas data. This is the energy resolution, which is one property of this hadronic shower. It's not important to give a precise definition of what is this energy resolution. The important thing is the procedure. So you make the ratio between simulation over the data. So a perfect simulation will be around 1, okay? So at that time, when this plot was made more than 10 years ago, QGSP BERT was the physics list that Atlas was actually using. It actually was the physics list that they used in the round one when the Higgs was discovered, for instance. But then we told them that given the improvement that we were made with this Fritty of FTF model, the model that I showed before, we were expecting that the FTF BERT physics list was actually better than QGS BERT. This was our suggestion, and by using the test bin data, they verify, and you see that this FTF, which is in red here, is closer to 1, which means that simulation and data agrees better than the case of blue, which is QGSP BERT. So based on this validation that they made, it's triggered by our suggestion, but these are their validation on their test bin data, they decide to move to this physics list. Indeed, in round 2 and currently in round 3, Atlas is using this FTF BERT physics list, which is our recommended physics list for high energy physics, and not any longer the QGS that was used before. So this is basically, you see, what we recommend as far as possible, the user to have to, follow our suggestion to where to start. But then, of course, always validate yourself if the physics list that we are suggesting is really good for you. And if not, try a different one or try to configure that physics list by adding other pieces or other switching on other option to have the best description of your particular data. And yes, the summary was basically, we are using this naming physics model. So in the context of hadronic, is an hadronic physics model, but also in electromagnetic, there are electromagnetic physics model. And in the case of hadronic, a physics model means a final state generator. So something that if I say 20 GeV proton on copper, it gives me some final state from that interaction. And there is no concept of cross-section, which is separate. Then we talk about physics process, something which is made of cross-section and final state model, and the two are separated. So the same hadronic cross-section can be shared by different final state models. And then the physics list, as we have seen, and we will see more on Friday, again, is a class which specifies all the particles which are present in your simulation and all the physics processes that those particles will undergo in your detector. And as I said, there is a trade-off between accuracy and speed. So that's why we are not providing a default. It really depends on a case by case, what is the best for your application. We offer some reference physics list, so some prepackaged physics list ready to be used. We give some indication which one to start according to your field, high energy physics, nuclear physics, medical physics, and so on. But then at the very end, you are in charge of actually validating this choice, hopefully with some data that you can have in order to decide which physics list and which configuration to use. So that's it from this part. So if you have questions, just let me know. Otherwise, I will move to the second lecture of today, and there will be plenty of time for questions later on. But if you have right now, do not hesitate.
There is actually one question, Matt,
yes,
from Franz Jacob. What would be the best way to modify a nuclear interaction model within a physics list? More precisely, is it possible to replace the cross-section values for a given interaction by user-defined values?
Yes, it is possible. Of course, first of all, GEM4 is an open source code. So you can do whatever you want. You can take anything, change it, do whatever. So it's always possible. This is not what we recommend. So the first thing that we recommend, if you see that the physics list that you are starting with is not working well, is not to put the hands inside the code, but to try different choices which are available, let's say, from Geon 4 directly, because this way things are somehow underwent to some validation and so on. If after that you try all the possibilities, still you see some disagreement and you are unhappy, and you have some ideas or you have some data that you think, for instance, for cross-section can improve the things, then yes, then you can look inside and do these changes. It's not something, again, that we strongly recommend, because you have to know what you're doing. It's pretty dangerous, you can make mistakes and so on, but it's possible, and there are people doing that. So, but you have to be careful. I mean, you need to look inside carefully the code, and it's easy to make mistakes. So before doing that, I would try, as I said, other possibility, like trying different physics lists, essentially. But there are people that are knowing what they are doing, and they are putting the hands and changing and using Geon 4 in their way.
Sorry, quick follow-up. Thanks a lot for your answer. I was just looking for, when you say look inside, maybe a first pointer to how to do that. Like technically, because yeah, I was expecting the framework to be flexible enough so that I could put my own values in, but I was hoping for some first step guidance on where to start to do this modification.
Yeah, there is not such a one easy guide, because it's a bit complicated, and it's complicated and depends also which cross section and so on. So my suggestion, you start from the physics list. From the physics list, you will see which classes are used, for instance, for hadronic physics. If you look inside that class of hadronic physics, you will see which processes are involved, and the process is made of cross-section and final state model, and you will see which cross-section you need to go. So
okay, yeah.
Possible. You need to look at the code. There is no, let's say, a simple guide that we explain, because this guide, it would be probably 1,000-page long, and we should rewrite it frequently. So it would be an effort that we cannot afford. And also, it's not something that we recommend to go in this way, to change, to put the hands and to change. So you have to do it if you really think you have to, and you have to have some knowledge, some expertise for that.
All right, thanks a lot.
You know, Gabriele, how to make it full screen now? To remove, I don't know if we are, yeah. Is it just this one, or? This I opened from the agenda, the PDF of the agenda. Or maybe, okay, good. Okay, so let's start the second lecture. So the first part was a reminder that we did already, so we can skip. And we go to the neutrons. So this again is a bit of a reminder of yesterday. We said that neutrons are really special. So there are plenty of them, and there are a lot of, it can go around for hours. It has a lifetime of 15 minutes, a free neutron. So many things can happen. Most of the time is having elastic scattering, and then it can have either it gets out of the so-called world, so the part that we are interested in the simulation, or it has an inelastic interaction in which it disappears, like capture or an inelastic thing. And below MEV, if we want to have a precise treatment, there must be, you know, a non-trivial model, not the default one, which is data-driven and depends really on the isotope. And this one is called HP for high precision. And as I said, as an exception, neutron doesn't have only elastic and inelastic, but there is also radiative capture and fission. So there will be 4 processes competing, each one with a cross-section, and the competition will be based essentially on the cross-section. And it is based, the treatment is based on so-called evaluated neutron scattering data libraries. And as I said already Monday, it is precise but slow. So you need to use it and consider to use it really when you need, typically for background, shielding, radiation damage, radio protection. Fortunately, it's not needed in most of high energy applications like the X searches, this kind of standard model analysis that are made in Atlas, CMS, and so on. And this HP you see essentially from the HP thing in the name of the physics list, with one exception, which is the shielding physics list, where you don't see HP, but is included. Now the new thing, I will tell you a little bit more in detail about this HP. So for several reasons, the data, mostly experimental data, is binned. So each time you, of course, bin a continuous distribution, you are making already an error. This data is also incomplete, so it's mostly inclusive data. So it tells you how often you get a particle with a certain properties, regardless of the rest of the interaction. So it's not taking into account correlation. Most cases, we don't have information on correlation. So because of these reasons, when you use NeutronHP, there might be some small non-conservation of energy, momentum, and baryonic number on the single interaction. You will have, on average, it is a Monte Carlo code, so on average, when you have several events, on average, you have conservation of everything, but not on the single interaction. So this is not a problem. The fact that you have conservation when you consider many events, but not in a single interaction, is not a problem for many applications, typically dosimetry application, medical physics or nuclear physics, where the most important thing is to reproduce the average, correctly the average value. Also for nuclear reactor studies, this kind, you care about the average, which is correct on the long term. But if there are other cases, mostly in high energy physics, for instance, where we want to have energy momentum conservation and baryonic conservation for each interaction. And in order to do that, given that the information coming from the experimental data is incomplete, we have to invent something. And in order to conserve the thing, what we do, we emit a fake gammas that somehow balance the energy momentum, but it's not a real gamma. So if you care really a detailed spectrum of particle, in particular low energy MeV range gammas, if you use this fake energy momentum conservation, you will see some fake gammas, and we get several from the user forum, several complaints about this fake thing. So our suggestion is, if you don't want that artificial energy conservation, like in nuclear physics, like in medical physics, we suggest to use this UI command. Do not adjust the final state true, which means that it takes really the information as it comes from this evaluated data. And as I said, you can have non-conservation on a single interaction, but on average, you will be guaranteed to reproduce really this accurate measurement that were made, most of them many years ago, but very precise on average value. The other important thing to keep in mind is that there is, so the cross-section value for these neutrons, this data-driven cross-section that we are using when we use HP, here I'm always using this NeutronHP in this discussion. These cross-section values are different according to the temperature of the target, okay? So the cross-section that we have in Gen 4 are the one at T = 0 Kelvin. So what's happening is that there is a a kind of on-the-fly calculation, if you want, which is called Doppler broadening, to take into account the real temperature of your detector. Let's say you have a room temperature detector. So there will be an operation each time to convert this cross-section, neutron cross-section at T equals 0 to the actual temperature of your detector. And this is quite, this is important, let's say, for neutron below roughly 100 keV. So if you don't care about this particle, given that this on-the-fly operation is quite computationally expensive, if you don't need, that means if you are not sensitive to neutrons below roughly 100 keV, you can switch it off via this UI comment, neglect Doppler broadening true. In this way, you will use the temperature at T equals 0, the one which are actually originally in our data sets, without any on-the-fly operation. Yes, so these data libraries are called in Gen4, are named G4NDL, Neutron Data Library, with some numbering, because we are improving and changing over the time. And the one which corresponds to 11.3, which is the one that we are covering in this lecture, is 4.7.1 and is based on JEF 3.3. JEF are the neutron library distributed by the European, by IAEA, essentially. Before that, we were using the American one. They were based on the NDF-B thing. And the reason why we moved a few years ago is that by using the JEF one, there are two advantages. First, we get better comparison, the agreement with the MCMP code, which is probably the most used code for neutronics, the code coming from Los Alamos, which is considered a bit the reference of neutronics. And moreover, by using this JEF cross-section, we get also the transuranic data. Whereas if you use the American one, of course, for proliferation, weapons, and so on, you will not get easily. You have to go through some kind of procedure. So whereas the European one are more easygoing, you can get also the transuranic that can be useful, for instance, for some application. Of course, peaceful application, we only support peaceful application. If you are interested for any reason to Gen4 data sets, but coming not from JEF or not for NDF, but also for other possibility like the Japanese Gendel, the Chinese Chendel, and the Russian one. If you go in this page from IAEA, you will have in the Gen4 format also the one corresponding to this library. Because what we are, these are libraries which are not directly usable in a Monte Carlo transportation code. So what is happening is that there is a transformation that every Monte Carlo transportation code does that transform this, let's say, native neutron library in a format which is convenient for Monte Carlo transportation. Each code does the same. And you can find the one usable for Gen4 for all of them, in the case that you need to do some systematic studies or for some reason you want to use one of these different ones. Otherwise, by default, without doing anything, you will get this G4NDL 4.7.1 when using 11.3, which is based on JEF 3.3. Again, remaining on this sophisticated, precise treatment of low energy model, for thermal energy, we said that this HP is used for neutron below 20 MeV. If we go even lower and lower and lower in energy, let's say below 4 electron volt, roughly, what is happening is that the wavelength of a neutron, the quantum mechanical wavelength of a neutron, is big enough to be sensitive not only to a single nucleus, but even the molecular structure of the thing. So you need to have, if you want to be precise, a special treatment, which is called thermal, it's called S alpha beta approach or thermal scattering law approach, which is based on both experimental measurement, also some molecular dynamic calculation. And there are separate thermal neutron scattering files coming from both JEF33 and the NDF B8 thermal data. There are roughly 30 materials. So this special treatment is not present for all materials, but also for materials where essentially it is important. Most of them are relevant for nuclear reactor, for instance, where there's been measured with great thing. So there are roughly 30 materials shown here. So if you want to use this thermal scattering, so by default, if you take an HP physics list, this thermal scattering is not treated. That means that below 4 electron volt, the treatment is approximate, is not very accurate. If you want that accurate thing, then you need to either take one of these HP physics lists and on top register this thermal neutron physics list constructor on top of your physics list. So it's one line of code in your main program. Or even more easily, this we added recently, starting with 11.2, you can pick up directly one of these HPT. You see an extra T, which means that this thermal treatment is enabled. And there is an example where you can see how to use it if you are interested. Moreover, there's been quite a number of recent refinements. So here is really details for those that really care about neutrons, low energy neutron. So first in 11.2, we have introduced an option. So these are all options that by default they are not activated. So there is an option to model really accurately the elastic resonance scattering of neutron in heavy nuclei. And it's called Doppler Broadening Rejection Correction algorithm. And this can be enabled via UI command. You see here, ParticleHP, use DBRC true. Another option, again, to be more sophisticated in the treatment of neutron, is to use NuDEX, nuclear de-excitation, which is a more sophisticated way to describe the nuclear de-excitation after, for instance, neutron interaction by emission of gammas and internal conversion electrons. This was introduced last year, and given that it's still, let's say, in the validation phase, it has been enabled only for neutron capture and only in this physics list, QGSP, BERT, HP. That is something that we consider experimental. I will tell you in a second why, and not yet fully recommended for physics studies. It can be enabled via this C++ line that you can put, for instance, in your main program. The third major improvement was made also last year, which again is optional, and it consists in the treatment of the unresolved resonance region via probability table. And this is relevant for shielding a nuclear physics application. And if you want to use this option, by default is not, you need to use a physics list constructor, this G4 URL neutrons, on top of any HP or HPT physics list. And so thanks to all these changes, now essentially the physics of Gen4 for neutronics is considered more at par with code which are specialized in neutronics like MCMP or Tripoli. So now we have all the ingredients. Of course, we need a lot of validation. For sure, there will be some bugs to be fixed, but at least we have all the components now, physics component, to have a really an accurate description of low energy neutrons. Moreover, we are also trying to re-engineer a bit the code, and we are using this QGSP BERT HP in order to do this kind of code development, not physics oriented, but really improving the code structure. And we are using that physics list. So be careful if you're using that physics list, your suggestion, your feedback are welcome, but not use it for serious physics study because it's something that we are still working on. Before leaving this low energy business, the NeutronHP has been also extended a few years ago, 10 years ago actually, also for charged particle, for proton, deuteron, tritium, helium-3, and alpha. And this goes up to 200 MeV. And this is of interest for essentially medical physics and nuclear physics. Is also a data-driven approach based on so-called Pendle database, which in turn is mostly based on a simulation code. So, and also from data, but the data is not as precise, as numerous as for the neutron. So there are really few experimental data. Most comes from a simulation code with all the limitation, of course, of simulation. And if you want to use it, you need an additional database that you can download in our site, G4 Pendle 1.4. And the two codes were initially separate, NeutronHP and ParticleHP. Now there's been merged, so now there exists only ParticleHP exists. And validation is still in progress. So far, we get good comparison with MCMP, which have a similar treatment. And now this ParticleHP is available only in this physics list, QGSP BIC all HP reference physics list. Be careful because we are still trying to understand. We got some user reports from version 11.2 and 11.3, where they report some weird behavior of this physics list. So we are still trying to understand and fix the problem, whereas it appears that using the older version 11.1, everything was fine. So we are still checking. So be careful if in the case you want to use it. Okay, now let's switch to the other second major topic. Then we will have a few other relatively small topics. So this is another major one, which is radioactive decay. So Gen4 knows about 6,500 nuclides, so different type of nuclei, with half-lifetime greater than 1 nanosecond. And this comes essentially from data sets, data files from the evaluated nuclear structure data files set, which are available. Roughly, there are 3,000 ground state and 3,500 metastable, so-called isomers, so which are metastable, so unstable excitation, if you want, of nuclei, but resisting somehow. In that sense, they are called metastable because they have a lifetime which is greater than 1 nanosecond, which is not negligible in the strong world, let's say, of strong interaction. Resisting more than 1 nanosecond is a lot. And there are two ways, basically, to have radioactive nuclides in Gen4. Again, either ground state or metastable. One is to use it as an input, as a primary particle, either at rest or in flight. And this is the way, for instance, that you can specify one of these isotopes, including also eventually their excitation, in the case that they are isomer, they are not ground state. And the other thing is this is direct. So you put as a primary one of those particles. And the other one is to have a so-called induced radioactivity or activation. So even if you have everything perfectly stable, let's say a block of iron, a block of copper, very stable, if you shoot a beam of proton, pion, and so on, through this hadronic interaction, at the end of the day, you will activate this detector. That means that following this hadronic interaction, you will get some of this unstable isomer, basically. And by default, essentially, this de-excitation nuclear model can create nuclides with a half-life greater than a threshold, which is 1 nanosecond. There is a difference whether radioactive decay is used or not regarding the way to change this 1 nanosecond thing. But the threshold is 1 nanosecond. Of course, if you are not using radioactive decay, this particle will not decay. So if you are not using radioactive decay and you are creating one isotope with a lifetime very short, it will keep flying, it will not decay. You need radioactive decay to have a proper, of course, treatment of the decay. So, so far in GEM4, we have the following types of radioactive decays: alpha, beta minus, beta plus, gamma, which is also called isomeric transition, and includes also the emission of electron, the internal conversion, which is essentially the emission of orbital electrons, but due to the nuclear de-excitation, not atomic physics. We have electron capture, proton, neutron, tritium, spontaneous fission. Not yet, but is on the pipeline to have also double proton, double neutron, beta delay emission, and double beta processes. And this is based on empirical data. So it's a data-driven approach. What is happening is, in most cases, you don't get one radioactive decay. You have one, then you come up with in a situation, in a stable situation, then there will be another emission and so on. You have a sequence typically of radioactive decay. And following this radioactive decay, you somehow excite and perturb also the electronic shells, the atomic electrons. So very frequently, almost always, whenever you have a radioactive decay process, which involves the nucleus, you then have also a set of emission, essentially X-rays, Auger electrons, which are then emitted in order to bring the stability, the ground state also of the electronic configuration around the nucleus. So for those nuclides, we have a half-life less than 1 nanosecond. These are forced to decay immediately, okay? We will not transport them. So we decay immediately below 1 nanosecond. And we use the photon evaporation class, which is used also for nuclear de-excitation, normal nuclear de-excitation. We have data for roughly 3,000 isotopes for more than 25,000 levels of those 3,000 isotopes with half-life greater than 10 to the minus 23 seconds. And of course, internal conversion, that means nuclear de-excitation via emission of orbital electron, via atomic electron, is also enabled. It competes typically with gamma de-excitation, competing the Monte Carlo sense. And there is option also to disable this atomic de-excitation in the case that you are not interested, but in general, it's good to have it. How much time do I have? According to the... Okay.
Maybe we take a question and then...
Yes.
Yes. There were already 3 questions, I think, it's been added to. Some of them, I'll take 1 or 2 of the more recent ones. You mentioned that something that I don't understand, writes the person. What is the typical energy scale of fake gammas produced to enforce energy conservation, which you mentioned?
It's MEV, around MEV.
Second question, does NeutronHP include neutron fission spectrum?
Yes.
And does ParticleHP cover alpha and neutron reactions in light nuclei?
Yes. Of course, as I said, experimental data is really sparse. Whereas for neutrons, there is plenty of data. For charged particle, the data is they are not so much. So there is a code called TALIS that is used whenever there is no experimental data. And sometimes there is experimental data, but for reason of security and so on, they are not shared and so on. So you can have a big discrepancy because the simulation TALIS, of course, it does the best that it can do, but there can be significant difference with the reality, I mean, in several cases.
There was an earlier question which we missed. What would be the best way to modify a nuclear interaction model within a physics list?
Yeah, that we
You
did.
caught it. Okay,
Yeah,
sorry. And there was a question about, could you please say about general neutron process? I see in 11.4 beta release notes that there are 2 bug reports which are resolved by the fact that it will be disabled by default in 11.4. Does it mean that the general neutron process is not used?
Yeah, so the general thing is so it wasn't, this concept of general neutron process is a way to speed up a bit the code. So it's a kind of trick to speed up the code and to have less individual neutron evaluation. So you bring together, instead of having 4 different cross-section, elastic, inelastic, capture, and fission, you sum them up. And when you compete with transportation and electromagnetic processes, for instance, or other things, you use this combined one. So it's a way to reduce the number of cross-section calls. So there is nothing deep apart a kind of trick to reduce the CPU time. And unfortunately, this brings some complications. And now I forgot, I don't know, but I think the 11.4 should be enabled, this general process thing. So I don't know. We can ask to Vladimir actually. I don't know if he's connected.
The person had some issue with it.
Yeah. So yes, we are aware that there were some problems with this general process. And yeah, I think if you can avoid to use it, I think it would be good because it's only brings, especially if you are interested in physics application, you don't care to be super performant, you know, the gain is really a few % level, so it's not a big deal. So I think if you don't use it, there is no big problem. I mean, it's for a large production where a lot, you know, you have to, like Atlas CMS, that generate billion of events, which make use this new general neutron thing. Otherwise, it's not that worth, I would say. Yeah.
Okay, 1 second. We have a local question.
Thank you. So my question is that regarding NeutronHP, you haven't mentioned the model NRESP71, which includes some final states about like neutron on carbon interactions.
Yes.
Like when 3 alpha is generated. So why is this model is not included by default or set?
Yeah, I forgot to include that. Thanks for reminding. I forgot about that. Yes, it is like is on the same line as the other one. I mean, no, I'm going the wrong direction. Yes, it's a kind of a refinement that is useful in specific thing. So we try not to put on by default to avoid that people are, you know, because it brings some overhead. All these options we are not switching on because they all bring some slowdown in the simulation. And the same is the one that you are mentioning. So unless you don't have a specific reason, you know, that you really want because you know what you're doing, then it's fine. That's why by default, they are all off. But here I forgot I should have included that one as well.
Thank you.
Okay, thank you. We can take a 15-minute break, maybe a shorter break today since we have a bit of a